In this video, we will discuss how to draw shear force and bending moment diagrams for beams. Well, you can do this by two methods. First, by cutting and determining the shear force and the moment mathematically for a distance x, or the second method, which is much more practical, is the graphical method. That's what we're going to discuss in this video. Beams are long and slender structural members in engineering, and if you have a loading on a beam like distributed and single forces, well, these will cause shear forces and bending moments, and the variations of the shear force and the bending moment are given by shear and bending moment diagrams. Let us discuss first the sign convention. Distributed forces towards the beam surface are positive. If you have internal shear forces, if these forces try to rotate the section clockwise, like here and here, these loads are taken as positive. And if you have moments which have negative, that means compression on the upper and tension on the lower surface, these internal moments are taken as positive. The graphical methods for constructing these diagrams. Well, we know that there are relations between the distributed force, the shear force, and the bending moment. These relations we will not derive, but just mention and make use of these relations. The first one, the slope of the shear is the negative distributed force. Let's take a point on the shear force diagram, and the slope of this point is equal to the negative of the distributed force. dV over dx is equal to minus W. Next, the slope of the moment diagram, let's take the same point, and this is my slope, and this slope is equal to the value of V at the same point. You see, if you move along the moment diagram, let's come to this maximum point. Here the slope is 0, as can be seen on the shear force. These are very useful relations. Next, on the graphs, for example, let's take the shear force diagram. When you move from point C to point D, there will be a change in the value of the shear force. This change is equal to the area, which is given by this integral, negative of this area. Similar to that, well, the change from C to D in the moment, which is delta M, which is equal to the area under the shear diagram. This area is the delta M value. Next, if you have a single force and a single moment, a force or a moment, then in the graph you will see a jump in the V values and in the M values. Okay, let's use this information in solving problems. Draw the shear force and the bending moment diagram for the beam. Well, we have a simple beam. In the middle, a distributed force W is acting. So this distributed force can be taken as a single force W L over 2. So this is the total force. Here we have two supports. Due to symmetry, well, these forces will be WL over 4. Now draw the diagram. Okay, we have here a force WL over 4 trying to rotate clockwise. So this is a positive. And here we have a force trying to rotate anti-clockwise. Here we have a negative WL over 4, positive WL over 4. And from A to B, there is no distributed force. We know that dV over dx, the slope of the shear force, is equal to W minus W, which is 0 for this region 1. So we have no slope. Well, same over here. But when you come to region 2, which is this region, here we have W. In this case, as you see, W dV over dx will be minus W. So we will have a negative slope starting from point B and going to point C. So this is my shear force diagram. Okay, that was the low. That is my shear force diagram. The values are here. Let's draw the moment diagram. Well, since we have pins here and here, the moments are 0. In region 1, the slope of the moment is equal to V, shear force. It is a positive value, so we go up with a value of WL over 4. And then from point B to point C, the slope or the positive slopes becomes smaller and smaller, goes to 0. Slope becomes smaller and smaller and becomes 0. And from here on, we got negative slopes. And here we have a constant negative slope. Okay, this is my moment diagram. How about the value of this M max? Well, we can do it with area calculation. This area is WL over 4 times L over 4, and that is WL square 16. And what about the next area? This one is WL for 4, and since this is a triangle, 1 over 2, and this time it's WL square divided by 32. And so from this point to this point, the total area is the sum of these two areas, and this M max will be 3 WL square divided by 32. Here you see it. Constant slope, positive, constant slope, negative. The slope drops, becomes negative. Here you have a maximum, and this we have calculated 3WL square over 32. And as you see, without any difficult mathematical computation, so we have our shear force and moment diagram using the graphical method. Next, shear force and bending moment. Here we have single forces. Here we have, of course, AY and BY, two vertical forces. In the X direction, there is no force at all. So you can take a moment around A and calculate BY, and the next is simple. So we will not spend time to do these calculations. Well, you can try it on your own, but the results are okay. So if you have this, how to draw the diagram? Well, here you have 50.5. Trying to rotate clockwise, we have positive 50.5. Here, negative 37.5. And starting at this point, here we have W0, slope is 0. And then a drop of 40. I drop 40 and come to 10.5. Again, here no distributed force. Slope is 0, and here 32. Drop by 32, I reach minus 21.5. And again, in this region, W is 0, slope is 0. Then a drop of 16, and I go down to 37.5. So as you see, we have our shear force diagram. Let's draw the moment diagram. So we know in point A and in point B, we have pins. These moments are 0. Here in region 1, the slope of the moment dm over dx is equal to v, which is equal to 50.5. So we have a positive slope. And in region 2, suddenly the slope drops to 10.5. And in point D in region 3, from D to E, we have a negative slope. And in the last region, region 4, we have a slope of 37.5. Okay, this is my moment diagram. Well, usually I'm interested in this value. So how you can do it, you can calculate this area. How can you do the calculation? 50.5 times 0.6. This is the first area, and 10.5 times 0.9. So if you do this calculation, let us do it. Okay, and here you have well, this is the result. You see, here we have the same value. Next, another beam, single force, distributed force. We have to find the support forces. That one is 46 and that one is minus 64. So let's begin drawing. This point is clockwise positive 46. Region 1, W is 0, no slope. Then a drop of 60. 46 minus 60 gives minus 14. Region 2, no slope. Again. Then in region 3, from D to B, we have a negative slope. Since the W is positive, dV over dx is minus W. That means minus 25. So with a slope of 25, you go 2 meters. That's a drop of 50. And from minus 14, we reach minus 64. This is my shear force diagram. And now the moment diagram. 0 in pin A, a slope plus 46, and then a slope of minus 14, and then a slope which starts with minus 14 and ends with minus 64. In region from D to B, the slope is at the beginning minus 14 and at the end minus 64. So this slope goes down and it becomes steeper negatively, and at the end our moment diagram like this. Okay, slope over here is 46, over here is minus 14. Here it starts with minus 14 and here it is minus 64. If you're interested in the maximum value of the moment, this area corresponds to 2 meters times 46 gives you 92. Here in this beam, the maximum shear forces are over here. Their value is 46 and the maximum bending is in point C and its value is 922 kilonewton meter. Well, a very similar problem, single force, distributed force, but this time we have a fixed support. Point B is a free end. So in such cases, we know that the critical point is always at the fixed support, and we can calculate the values, the moment, and the shear force at this point. So all you have to do is to take a moment around A and to take a sigma Fy, and with the help of these equations, you can find that M and F values in point A can be as 6.24 and 4.6. And now let's draw the diagram. Well, here in point A, I have a force trying to rotate clockwise. That is positive 4.6. Region 1, no slope, W0. Then a drop of 3, so I reach 1.6. Region 2, slope is 0. And in region 3, we have a slope dv over dx is minus 1. Well, we know that here w is plus 1, but dv over dx is minus w. So with a slope of minus 1, when you go down 1.5 meters, then starting from 1.1, going down, you reach the 0. So your shear force will look like this. Next, the moment diagram. Here my moment is a moment trying to bend the beam like this. You have positive in the upper, negative in the lower surface. So this is a negative moment. We remember the sign convention. Such moments are positive, such are negative. So we start with a moment. What was its value? 624 minus. As you see over here, at this end, at the free end, well, it should be 0. So here, the slope is 4.6. So we go up with 4.6. And suddenly the slope drops to 1.6, and then from 1.6 the slope drops to 0, so it looks something like this. As you see, the diagram in this region, slope at 4.6, here 1.6, here it starts with 1.6 and goes down to 0. Okay, so the points are very clear. As I said in the beginning, it's at the fixed support, but we have the values and the distribution of V and M. Next, shear force and bending moment diagram for this beam. Distributed force, single force, and there is a single moment. Now, instead of this distributed force for support force calculation, I put 40 times 8, that is 320 kilonewtons, and AY and BY are my support forces. If you write the moment for MA, you find this value, that is BY. So you do the calculation sigma Fy is equal to 0, then you find the AY value. Now we have everything, the external forces and the support forces, so we can draw our diagram. Well, V diagram here we have positive 132.75. In region 1, in this region, we have a positive W40. The slope of shear force is negative 40. How long? 8 meters. So starting from here, I go down with a slope of 40. Well, the total value I go down, it will be somewhere here. Okay. Well, there you have suddenly, well, that is 180 something. And in this point, in this port B, I have a force of 200. So I jump up 200. It will be 20. And in region 3, this region, your slope is 0 and you reach this point. You see, this is my shear force diagram. Next, the moment. Well, over here 0. And at this end, I know that it is for a moment trying to bend like this, 150. Well, since it's positive in the upper and negative in the lower side, this is a negative moment. So we will have minus 150 over here. Now, start with point A. What is the slope in point A? It is 133. So it becomes, when you move to the right, the slope dm over dx is w. The value of w, of v drops. So at this point, it is 0. So it becomes 0 over here. And from here down there, as you see, it goes with getting steeper slopes to this point. And when it's down, then after this point, your slope becomes plus 20. So it goes from here with a slope of plus 20 to the free end of this beam. Looks like this. So as you see, at this point, slope is positive. At this point, slope is 0. Here it's negative. Here the slope is constant, plus 20. Here the moment is 150. So when you are interested in calculating the values, you can do the following. Well, this is the maximum. Okay, you can calculate this triangle, and we will have a positive value. And when you're interested in this value, then you have to calculate this negative area. So starting from here, with this negative area, you go down to minus 210, and that will be the solution for this problem. I think this is the last one. Again, single force, single moment. I need to calculate the support forces AY and BY. Not spending time for this. With equilibrium, the values can be found as 3.75 and 3.25, and let's draw my diagram. As you see, here I have a positive 375. Then here I have a negative 325. Region 1, slope is 0. Minus 7, when you go down 7, well, you will get minus 3.25. And from here to there, in this region, region 2, well, you will have 0 slope, and the curve will look like this. Okay, let's draw the moment diagram. 0 on both supports. As you see, in this region, your slope is equal to V, which is plus 375. The slope is 375. You reach this point, and after this point, in region 2, the slope suddenly becomes minus 325. So, well, here, well, if you go 2 meters with 375, you reach 7. When you go down with a slope of 325, 2 meters, that's 6, so you reach 1. And as you see here, you have suddenly a jump in the moment 12. So you come to the point 13, and starting from 13, you go down with a slope of, again, 325 for 2 meters, 13 down to 0 in 4 meters with a slope of minus 3. As you see, this is how it looks like. And we see we can calculate this value, this area, minus this area gives you 1. And plus this 12 gives you this one. As you see, the shear force and the bending moment diagrams can be easily calculated with the help of graphical methods. But not each loading condition can be solved graphically. There are cases where you have to use both the cutting method and the graphical method together. Okay, that was our video about drawing drawing the shear force and the bending moment diagrams graphically. Thank you for listening.